In this video, we're going to take a quick look back at functions, what they are, how we use them in math, in order to build a foundation from which we can start to construct this idea of calculus. A function is quite simply something that when you give it an input, it gives you some type of output. And so in math, we call the inputs the domain and the outputs the range. So we have a function that tells us when we put in a number, we do a few things to it, and it's going to spit out another number. The math definition of a function is that a function f is a rule that assigns to each value x in a set D a unique value denoted f of x. We'll talk about why it's unique and how important that unique thing is in a moment. But the set D is called the domain, and the range is the set of all the values of f of x produced as x varies over that given domain. One of the ways that we can test if something is a function or not is using the vertical line test. Over here we see that we do not pass the vertical line test because we cross through this relationship twice with one vertical line, whereas this we do pass the vertical line test. So this is a function, this is not a function, or at least over here y is a function of x, whereas over here y is not a function of x. So the vertical line test helps us when we're given a graph. You've done this all the way back in Algebra 1. Looking at an example here, we see that this does in fact pass the vertical line test. It is a parabola, that is a function. This does not pass the vertical line test because we can draw a vertical line and we hit at 2 points, so not a function. This graph here, it does twist and turn, but it is a function, and this curve here is not because it does not pass the vertical line test. Even though that line is not very vertical, we still see that it does not pass the vertical line test. As stated before, the domain and range come in here with the function. Domain is our input value here. That's also the x value in our standard Cartesian system. X corresponds with the domain, all the values that we can have for x. And the range tells us the values of y that we're going to have after we evaluate whatever x is. A way to think of domain and range physically on a graph is that the domain is how wide the graph is going to be, and the range is how tall the graph is going to be. The values of, in this case, the z, the lowest z to the highest z. So given the function z equals the square root of 4 minus t squared, well, we know t can only be from -2 to 2 in order to keep these numbers real. Outside of that, we're going to get unreal values for z. And so our domain is constricted, and consequently, our range is then constricted in that z can only be a maximum of 2. Unlike the last example, this one actually goes on forever in that we don't have a maximum domain value. We can have any x value as far to the right as we want, or in this case, it's a u value. And we can have any value we want to the left. However, there is an issue at this value of 1. Why is there an issue at the value of 1? Well, that gives us a 0 in the denominator, and that is a big no-no in algebra. Now, as we get into calculus, we're going to look at ways to interpret what actually happens when we attempt to divide by 0 and all the tricky stuff that comes with that. But for right now, when dealing with functions, we say that, well, this function is not defined. Its domain does not exist at u equal to 1. Well, consequently, the range is going to also go to an unbound value in the positive direction and an unbound value in the negative direction. However, we see that there is a hole here in that we can never get an output of a value of 0. And we call these two things graphically asymptotes, or we say that this function has asymptotic behavior as u gets positively huge or negatively huge, as it's going to a very high positive number or going to a very high negative number, or in other words, a very low number to the left. We see that our function levels off at 0. Never quite gets there, but it approaches 0. Let's put this domain and range into context here for a moment. And let's say that we have at t equals 0, a stone is thrown vertically, and we're going to throw it vertically upward from the ground, and let's say it's at a speed of 30 meters per second. So we're throwing this stone vertically upward at 30 meters per second, and its height above the ground we can measure with this function here of 30t minus 5t squared. And we're talking about that's going to be in meters here. All right, so this describes, as a function of time, how high this stone is. Now, we're not talking about left and right, just because we see this parabolic path. This is not the path of the stone. We're just throwing the stone up vertically and then catching it or letting it hit the ground, whichever. And so this graph is depicting how high is the stone at any given time. So we can evaluate to say, well, at 1 second after we launch, where is this thing? Well, we can follow up and we see that we have a height of, somewhere between 20 and 30. And then what about at 2 seconds? Well, we evaluate up and we see that it's at 40. And we can continue this, and for any given domain, we can then find the range, the output. And we can see that, well, what does our domain go to? Well, it goes from 0 over to 6. Now, you may ask, well, why do we have those restrictions on the domain? Couldn't it be -2 or 7? And just looking at the function, yes, it could. There are no restrictions on the function itself. However, when we use these functions in context, for instance, this is time, time cannot be negative. And at t equals 6, that's when the stone hits the ground again. Well, after the stone hits the ground, it's not going to continue into a negative height. It's not going to burrow itself into the ground. So those things just don't make sense, so we eliminate those from our domain. So in this case, our domain is just 0 to 6. Now I'm going to pause here for a moment to talk about some notation. And I'm not sure if you've seen this notation before, but this is a type of notation that I will require you to use throughout this course. When talking about the domain of t, so we want to say t is defined as, now this sign right here, this is a little epsilon, it's a Greek letter, okay? And so that's going to tell us that t is defined on the interval from 0 to 6. All right, now notice these are brackets here because we're including both 0 and 6. You may have had some notation like this, but this is the way I want you to denote. Not as an inequality, I want you to denote it as t is defined on the interval 0 to 6. Now if we want to talk about the height, well, what is our maximum height? Well, our maximum height is up here. And we know that that max height is going to happen at 3 based on the graph and some other techniques that we can use and we'll employ later. But we see that, okay, at 3, we're going to have a height of 45. So what is our height defined as? What interval do we have for our height? Well, we go from 0 to 45, and we include both of those, so we have brackets for both of those. When dealing with functions, we have this idea of composite functions or functions inside of functions. And so if we're given two functions f and g, the composite function f of g is denoted by either f with a small o g of x or f of g of x, where g of x is just inside of the f function. It is evaluated in 2 steps. So you first have to find the u of, well, what is g of x, and then we're going to plug that back into f. And the domain of this composite function, f of g of x, consists of all x in the domain of g, such that we've defined that u is equal to g of x is in the domain of f. So there's a lot going on there, and we need to unpack that and make sure we understand what that means. We first look at the domain of g, and that restricts our domain. So any restrictions we have on g, those are the only possible x values that we have for this composite function. Now, that domain is going to go into g and spit out this range here. Well, f in and of itself also has its own domain, and only where these two overlap, that will then be the domain of our composite function. And then this spits out its own little range, which is the f of g of x. We can evaluate these composite functions from either function rules, such as f of x is equal to 3x squared plus 1, and g of x is equal to 1 over x minus 2, and we can evaluate what is f of g of 3. Or in another case, we could be given a graph, and so we don't have a function for f or g, but we do have a picture of the function for f and g on the interval where x is defined from 0 to 9. So we're given f and g on this interval from 0 to 9, and so I could ask, well, what is f of g of 2? And in order to evaluate this, I'd have to look at, well, what is g of 2? Well, I look at 2 here, and I see that g of 2 is 3. And then so if I know that g of 2 is equal to 3, so then I need to know what is f of 3. Well, look at 3 here and go up to f, and I see that that's equal to 5. So that means that f of g of 2 is equal to 5. One of the big concepts from algebra and pre-calc that we are going to use heavily in calculus is this idea of the secant line. So if you've been zoning out for the first part of the video, pay attention to this part right here. This is an important part. We need to know this idea of a secant line, and then that's going to get us into this concept of a tangent line, which is really the basis of the building blocks of calculus. So what is a secant line? Well, a secant line is where we have a function, we have 2 points on the function, and we connect those 2 points with a line. And so finding the slope of that line, we know we can use our typical rise over run techniques, y2 minus y1 over x2 minus x1. Well, I'm going to show you a formula that's a little different, but it's the exact same concept. This formula here is still rise over run. It's just, it looks a little different. And this format of the formula is vitally important to what we're going to do here in calculus. So if we examine the top of this formula, we see that it's asking us to take f of x plus h. Well, what is this x plus h? Well, we have some value x, and then we're going to add a little extra to it to get x plus h. Whatever h is, doesn't matter. It's just going to make our domain value a little bit more than x. And so when we evaluate our function at that little bit bigger x value, and we subtract our function evaluated at that original x value, that gives us the rise. That is our change in y. Notice the Greek letter delta here to signify change. That is delta y up top. And in the bottom, well, what's that? That's our run, which in this case is delta x. It's our change in x. If we take x plus h minus x, we are left with h. And so that is our formula for a secant line of any function. Doesn't matter what the function is, this formula can help us find the slope of the secant line. Another way to write this, and I know it may seem a little redundant, but these two formulas are very important, and the way we write these formulas are very important for calculus. So looking at the secant line, we could say, well, instead of x and x plus h, let's just call the starting point a, and then our ending point is going to be some value x. And so to find the slope of the secant line there, this is truly the y2 minus y1 over x2 minus x1, where we just take, well, evaluate our second x value into the function, subtract evaluating the first x value into the function, and find the difference of the x's for the denominator. So this is still delta y over delta x. It's just written a little differently, and the purpose for that you will see later. We call this slope of the secant line the difference quotient, and it is also the average rate of change. So one of the things that I'm going to really stress to you in this course is not just knowing how to do things, but why and what is it. So you need to know what is the slope of the secant line. When you hear slope of the secant line, you should think average rate of change or a difference quotient. So to illustrate that relationship of what a secant line tells us, what we have pictured here is a graph of sound intensity I as a function of the distance you are away from the source r. And that function I as a function of r is given by p over 4 pi r squared. Now, that p is going to tell us the power. So the more powerful the source, the more intensity that we're going to have, basically. So for any given power of a source in watts, we divide by 4 pi times the distance away from that source squared, and we can get our intensity of the sound. So if we were to look at the intensity of the sound when someone is standing 10 meters away as opposed to 15 meters away, we can evaluate in this function, and we see we get 1 over 4 pi and 1 over 9 pi. And looking at the secant slope, we get a negative 1 over 36 pi watts per square meter per meter, all right? And so what this is telling us, it gives us a little bit of an idea of, well, what's happening here as we move from 10 to 15. Well, first off, this is negative, so that tells us that we have an average rate of change that is decreasing. And so that's important. You need to be able to interpret what these numbers are telling you. And so we see that it's negative, and we get a relative size, 1 over 36 pi. It's kind of a small number, but it gives us an idea of the average rate of change of the decrease in the intensity as we move from 10 meters to 15 meters away from the source. With functions and graphs, we can have symmetry, and it's important for us to be able to identify how things are symmetric, when they are symmetric, and why they are symmetric. And so we can have symmetry with respect to 3 different things. We can be symmetrical about the y-axis, symmetrical about the x-axis, and symmetrical with respect to the origin. This parabola here is symmetrical about the y-axis or with respect to the y-axis because we see that the old elementary school definition of symmetry, if you fold the paper along the y-axis, the graphs will line up. Or in the math terms, well, when we have the negative of these domains, so if we have opposites in the domain, they yield the same range output. So for negative 2 and positive 2, you're going to get the same y value. Negative 10 and positive 10, you get the same y value. Any function that does that is symmetrical about the y-axis. Likewise, we can have symmetry about the x-axis, where for any given y value and its opposites, we get an x that is the same. Now notice the change in the way I said that, in that y became our input. And so if y is our input, then that changes the y values to the domain and the x values to the range. And typically we always say, oh, the range is the y values and the domain is the x values. Well, that's just in our typical Cartesian system. That's when y is a function of x. But in this case, we know by the vertical line test, y is not a function of x. However, by the horizontal line test, we do know that x is a function of y. And so typically, things that, well, not typically, always, when things are symmetrical about the x-axis, y is not a function of x. However, x could be a function of y. All right, so just having symmetry about the x-axis does not determine functionality, but that does open up the possibility that x could then be a function of y. The last one is symmetry about the origin, and this one's a little different in that when you have x, y, so some value x comma y, we find the same value of negative x, negative y. And so if we have the point, say, 3, 2 over here, the point of negative 3, negative 2 is also going to exist in the third quadrant. We actually name these functions that have symmetry in that we call functions even if we are symmetrical about the y-axis, whereas putting in a negative x value into the function is the same as putting in that positive. So we call that an even function. Easy example of that, y equals x squared. Put in a 1 and a negative 1, you get the same thing. Put in a negative 4 and a 4, you get the same thing. It's symmetrical about the y-axis. It is called an even function. All right? An odd function has the property that when you put in a negative into the function, the negative kind of pops out. So an easy example of that is y equals x cubed. Put in a negative 2, you get negative 8. It's the opposite of putting in 2. where you get positive 8. Put in a negative 3, you get negative 27. Put in positive 3, you get positive 27. So we have that relationship, and we know that that is symmetrical about the origin. Now notice, even functions, even exponent. Odd functions, odd exponent. Not a coincidence there. That is where the names came from. But we are not limited to polynomials. You should know from trig that sine of x, y equals sine of x, is symmetrical about the origin. So that is an odd function. Y equals cosine of x, that is symmetrical about the y-axis. So that is an even function. So we are not purely limited to polynomials for even and odd and this symmetry. Not all functions are classified as even or odd. This function pictured here is neither symmetrical about the y-axis nor is it symmetrical about the origin. So it's neither an even nor an odd function. It's just a function. Now you might say, well, wait a minute, it's cubic, it's a polynomial, wouldn't it be odd? Well, if it were just y equals x cubed, or if we would change this so we could get it so it's symmetrical about the origin, then it would be an odd function. But because of this piece, it shifts the cubic function over and up a little bit, and so we lose the symmetry. It is no longer an odd function.